Hi, so here we are again at this is session number 3, and during lunch I thought of something that I wanted to mention in session number 1, and it's just a little bit of my personal feelings about how what I hope that, publishing this whole program will achieve. I learned programming myself by reading other people's software, reading listings of software when I was a college student. And some of the software was very good for me because it was badly written and gave me a lot of motivation that I said this was written by a professional and I could do better than that, so I must have a special talent for it, so I'm going to major, I'm going to become interested in computers. And others of it was very beautifully written, and I thought this is a pleasure to read. I'd like to do something like that someday. Now, I'm not sure which category this particular program is going to fall into, but either way, you seem to be winning, and you could reach the right person. You know? So I'm hoping that some people, young people, might see this program and learn from it at least one aspect of software writing. And I'm not sure exactly if this could be used in curriculum, or if it's just something that people would do during the summer, or on their own to pick up. But somehow one of my goals has been to provide a picture of software here in a way that might inspire some people out there to write their best software. Now, the agenda for our afternoon, the next thing is called Data Structures for Boxes and Glue, and this is one of the key things that used over and over in TeX. The way boxes, lists of things are represented there. So, as I mentioned in the last lecture, a large part of the memory, a large part of the core memory that's going on while TeX is running, more memory than in fact the whole program itself, is this dynamic memory area. This is where we're going to store things about boxes and glue. Really horizontal lists and vertical lists, and the elements of horizontal lists and vertical lists can include boxes, glue, and a variety of other things. So now the first thing we have to understand is the way that memory array works, and so step number 1 is to see that every item that you address in the array is what we call a memory word. It's a Pascal record called memory word, and this is it's in module 105 on page 37. Now, a memory word is something that ought to be represented well by your Pascal compiler. If you don't have a Pascal compiler that's going to do this memory word correctly, you can be wasting an incredible amount of memory. Well, a factor of 4, probably. So you'd like to have a Pascal compiler that packs things properly to a memory word. Now, when I have something of type memory word, it's a variant record. The definition is actually on page 38. So let's look at the whole definition. It's in module 108. It's where let's see, we might get it on the screen. So we have memory word is made up of 4 quarter words is one of the options, or 2 half words, and so we have a definition there that says 2 choices, 4 choices. This is just because of the way Pascal is. I needed this particular type. But a memory word then is a packed record, and then it's a case 4 choices of. This in Pascal means that there's 4 possibilities, and if you store something under any one of these, you should retrieve it under the same one. So if I set x.int to something, it ought to be an integer, and then I shouldn't try to read out x dot GR. I should, unless I'm using dirty Pascal would allow me to read out x.gr. And this is called a variant record, and it's a special case of a variant record where I don't store the particular variant. Some people would put in there, store an integer 1 to 4 with the record, with x, so telling what kind it is, but that wastes space and time, and there's no point in it the way we're using it. So we have 4 choices: int, gr, hh, and qqqqq, of 4 different types. So this memory word is supposed, for all 4 different types, they're all supposed to come out to be approximately 1 word then of memory. We'll talk about these types in a little bit. There's actually a 5th type that I use in the program called SC, and that's because I also have scaled quantities. This is a section that I didn't discuss. It's the previous section of the program. Scaled quantity is an integer, but it doesn't represent an integer. It represents a unit of, it represents a physical distance. So it has units, and the units are scaled points, namely 2 to the 16th scaled points makes 1 point. That's scaled point then is, so if a word is scaled, that means that a decimal point is 16 bits from the right-hand edge. And when something is an integer but it's really representing scaled, I call it SC instead of INT, or I say that its type is scaled instead of integer in order to provide a comment to the reader about that. Pascal never sees this, but the person reading this program gets to see the difference between SC and integer. Now, all of these are supposed to take up the same space. I worked it out so that TeX will never allow the user to give it an integer constant greater than 2 to the 31 minus 1. So or less than negative of that. So this means that TeX should be able to work with 32-bit integers that have signs. And if you have a machine that has more bits than that, well, you still run TeX, and those other bits will presumably be 0. However, you could get actually larger integers in there through some arithmetic operations, and they just would overflow on machines that are smaller. But we would prefer that people write TeX programs that are going to work on all the 32-bit machines. If you have a larger machine, what you should do with it is make your quarter words and half words bigger, so that gives you a chance of making the mem array bigger. Then you can address more words, but not actually work with bigger integers or scaled values. You don't really need anything more, any dimensions that large inside a typesetting job. Who's going to typeset something more than 19 feet? One thing. So we're at least if you wanted to, you could probably break it into 2 parts or say that it was. Or magnify it up from something else and have the magnification done in the DVI file. So 32 bits is plenty for these integers. Now, glue ratio is the next case, and that is something that you could define any way you want to. It's defined here as real. Now, a glue ratio is used only to when we're setting a box and we have to stretch or shrink the glue. Then the glue ratio is the proportion by which the thing will stretch or shrink. So if we're stretching, for example, and the glue ratio is 0.333, then 1/3 of the stretch component gets added. And I distinguish between that and scaled. The scaled values are kept as integers, and the arithmetic is defined very precisely on all the scaled values, because it's important that every implementation of TeX compute exactly the same numbers when it works with scaled values. Scaled values will affect the performance of TeX as far as how many lines get put onto a page, and how many pages there will be in a manuscript and so on. If you stick with the calculations as they're given here, you can be sure that you will get the same typesetting information on a CDC machine as you would get on an IBM machine. Even though their arithmetic is done quite differently, they at least agree on integers. But when you try to tell them to do floating point arithmetic, you're liable to get all kinds of different results. And this would lead to different typesetting, different pages, and people sending tech job from one place to another would find that it doesn't work out. So this is a major change that I made in TeX82. That was, at first, it was going to be the only major change. But we felt quite strongly about it as being one of the first noticeable defects in TeX, that we weren't machine dependent because we were depending on floating point arithmetic. So I went to scaled. However, for glue ratio, it was a big pain to work with scaled numbers and doing multiplication by so many ratios, which you had to do in simulating multiple precision in order to get a decent result in all the cases. And really, it wasn't necessary because the result of a glue ratio never participates up front in TeX decision making. It only comes out when you're setting the final box in outputting to a DVI file. Does it actually ever compute this number from the glue ratio? So I can use real arithmetic, floating point arithmetic, in other words, even though it's not machine independent, because that will only affect the positioning of the final boxes in something that the eye couldn't possibly detect. So you can use that there. If you want, however, to do fixed point arithmetic instead of floating point, for example, you're implementing this on some kind of a micro that doesn't have floating point, or it has horrible floating point software, then there's a suggestion for how to do all the computations you need with glue ratio in something that would pack into a word, 32-bit word, and I wrote that up in Tugboat, and that appeared in I think the February issue of Tugboat, and I have a reference to it actually in the program somewhere. Glue ratio, here it is. Tugboat 3, 1982, pages 10 to 27. It's a reference in module 104. So that's the type glue ratio, which I've made real in this case. Now, if you change it to some other type, then you just need to find a few places where I've used glue ratios. I have to print a glue ratio. I have to multiply by a glue ratio, and one or two other things. And then you could substitute something there that would be probably better than a bad floating point implementation if you had to do it on a micro. Now on IBM Pascal, at least the way it was some time ago, if you said real, that would give you 64 bits. So you'd have to say short real in order to get a 32-bit floating point number. And person should be careful to declare memory words so that this will work out. If glue ratio was real, and then integer would be 32-bit, but you'd still be wasting 64 bits for every memory word because it picks the worst case of these. Now, what about two halves? Here's another common thing where we're going to break up this word and pack two different things in the word. So two halves is defined up above that, and it's a packed record also that has a RH, which you might realize is right half. And then the other part of it is either LH, another half word, or two quarter words. So the RH is always a half word, but with an RH you don't necessarily have an LH. You might have two quarter words, B0 and B1. So that's the two halves type. And that two halves type is quite commonly used, especially in the whole upper part of mem is entirely two halves, as we'll see. Now the other possibility is four quarters, and that I think you could guess. It's B0, B1, B2, B3, all quarter words. Now some machines will pack a quarter word if it goes in the range 0 to 255, say, and if you have a 32-bit machine, you'll be able to get 4 quarter words in one word, and they'll be treated as from 0 to 255. But on other machines, the only way they would pack is if it was like minus 128 to plus 127. What's happening here? We're losing the screen. I think you better leave that down because I might get back to it again. It's fun to watch it, isn't it? So on a Pascal implementation, that if you give it 0 to 255, if it considers that a 9-bit position, then you wouldn't be able to put 4 of those in a word. And on the other hand, on our Pascal, if you say minus 128 to plus 127, it takes up a whole word for that. It considers that a sign position has to only go there. So Pascals are quite different from each other, and I didn't want to make TeX unusable just for that fact. So I defined quarter word in a very general way, where it's a subrange from min quarter word to max quarter word. And similarly, half words go from min half word to max half word. And you can redefine these, and chances are TeX will still work. Now I'm going to have to debug it with min quarter word non-zero to make sure that I've not forgotten to add it in the right place and subtract it in the right place. Because what I do is, if I want to represent a number from 0 to 255 in a quarter word, I subtract min quarter word from it. Or no, I add min quarter word to it, excuse me. And then when I read it out, I subtract min quarter word from it. Now, the conditions that those constants have to satisfy are all listed there in 106. So all the program is supposed to work provided these conditions are true, and the program actually runs through and checks those conditions. Any TeX does anyway. Checks these conditions and gives you a stop at the beginning saying, sorry, but you set up your you set this thing up wrong so that I can't handle it. The conditions are, first of all, that your min quarter word has to be 0 or negative. You can't have min quarter word equal to 1 because I'm storing 0 sometimes in a quarter word. Okay. Similarly, max quarter word has to be at least 127 because sometimes I'm storing 127 in there. And okay, min half word has to be again 0 or negative. And the maximum half word has to be at least the largest 15-bit number. Then we also have to have a relation between quarter words and half words, that any quarter word can be storable in a half word. So that the next line says that the minimum quarter word has to be greater or equal to minimum half word, and similarly for the maxes. The next line says that the memory base, that's the lowest address in memory, has to be greater than or equal to a minimum half word, and the largest address in memory, mem max, has to be strictly less than max half word. These are the cases, the relations here are not the ones that must be true, but the ones that must be false. So mem max cannot be greater or equal to max half word. The max half word itself is used as a flag, so the largest location addressable in memory has to be strictly less than your maximum half word. So for example, if your min half word is minus 2 to the 15th, your max half word is 2 to the 15th minus 1, is 32,767, then your mem max had better not be any larger than 32,766. If you have a 36-bit machine, you see, you could make your max half word 2 to the 18th minus 1, and then your memory max could be 4 times as large as on a 32-bit machine. Similarly for fonts, so the gist of that line there says that any memory address can fit in a half word. So I keep pointer data, pointers to memory locations in a half word. The next line says essentially that any font, internal font number can fit in a quarter word. My internal font numbers are the numbers that I assign to fonts, not the user's number, but the one that TeX keeps. The user might have several fonts, 10, 11, and 12, that all turn out to boil down to exactly the same font, and I'll map those into the same number. inside. So I have an internal font number, and besides, his numbers might range from 0 to a very high case, but I want to pack them all tightly. Internally we have numbers running from font base to font max, and those numbers, internal font numbers, must all be representable in a quarter word. The next thing is similarly things I want to represent in a half word. The save size, that's usually very small, only a few hundred, but if it were larger than a maximum half word, I'd be in trouble. So I put all those restrictions that would conceivably ever cause TeX any problem. I think I listed them here. And so you're not allowed to have more than, say, 32K strings. Now that's not the size of the string pool, that's the size of the string start array. That says that you shouldn't have that many strings. Well, it's rare to have more than 10,000 strings. Who would want 30,000? I mean, because each one of those strings would be pretty long too. So if you can't get that in a half word, you're in trouble. I doubt if anybody would ever set max strings that high, but if you did, they would say bad with 16, and later we get an error message saying this is case 16 of what you can't do. This error message is expected. See, these error messages are expected to come along so rarely and seen only by a person running any TeX that they have just been left as numeric codes. The last one is a buffer size. Your input buffer, which I have at 500 now, and that's been more than enough. If that gets larger than 32,000, then that'd be bad, because I'm storing a buffer pointer somewhere in a half word in at least one place in TeX. Okay, so those are the constraints there. And you want to design those so that so that it all gets packed together. Now, Pascal compilers don't always optimize adding 0 and subtracting 0. And my program is careful to add min quarter word and subtract min quarter word and half words and so on, especially this quarter word, every time that I'm packing something that might go past 127 into a quarter word. Well, this is in the inner loop. I mean, like every character, this happens to every character. And so I'd be adding 0 and subtracting 0 rather needlessly in the part of TeX that's supposed to run real fast. I believe we've made memory counts before, and I think it'll still happen in the new TeX, that a very small part of TeX, maybe 1% or so, is executed a large number of times. And I call that the inner loop, and we make pains so that the inner loop doesn't have a lot of wasted motion in it. So because if the inner loop is fast, then I can do just about anything everywhere else, and it won't make much difference. So one of the things we're doing in the inner loop is adding and subtracting min quarter word. So I define macros for this purpose. There's the QI macro for into a quarter word, and QO macro for out of a quarter word. And they just add and subtract min quarter words. This is in section 107 here, you see. Now, of course, in my change file at sale, min quarter word is 0, so I've just redefined QI of hash to be hash. Because this Pascal wouldn't optimize away that 0. And that'll make TeX run maybe 5% faster. So it's changing that one macro. Now if I've missed it somewhere in the program, saying QI where I should have, I won't notice it right now because QI of something is, leaving it out would have been the same. So I'm going to run some tests where I have min quarter word negative, and that means that my memory words are going to not pack into one word, but that'll be okay because I can run tests on a small memory size to check that. But you won't have to worry about it. I'll be the one that has to worry about this kind of testing. Any questions on this part now? You think you understand what a memory word is? Yeah, question?
Yes. Should we change this?
Please use the mic.
Should this piece of code then be change those macros, in other words, at our compile time?
Yeah, in your change file. Yeah. See, I'll put that up on the screen. Let's see if we can switch to the computer file here, and I'll search for QI left bracket. Okay, here's the change that I made at sale for this. And so you see that with all changes, the top line is common to the two, and then I added this other sentence here. So they have been simplified here in the obvious way. And you see how I did it. Can you read a web source file instead of a web output file? Is it sufficiently enough contrast there? You see, you put a @D for a definition. So that's what you do. Okay. Now, while I'm at this, I guess I could explain that that I have a last resort thing for debugging built into the TeX debugger, and let me see if I can activate that. Let's see. I'll run a preloaded version of TeX. This is TeX that's been preloaded with a format from the trip file. Yesterday we played around with the trip file. It has the Pascal debugger in it, so I have to do this to get out of the Pascal debugger. And now it's running this TeX, and it says format equals trip 82.725, which is probably last Sunday. And now to get into my debugger, I have a TeX debugger built in also that will do things in TeX. So TeX debugger, I can, for example, give an undefined control sequence, and it'll stop on an undefined control sequence. Now, when I've compiled TeX with the debug switch, debug and GUBED, or whatever that debug backwards is, if I've not commented out the debug code, then I have a special secret option that I can type to an undefined control sequence. However, I'd better get out of scroll mode before I do that. Because I'm in scroll mode that doesn't allow me to respond to undefined control sequence. So I go to error stop mode and give another undefined control sequence. Now I got a question mark prompt, and so I can say D. This is the secret thing that I can do, and that gets me into my debugger. Now the debugger is written at the very end of your program. It's module. Maybe not the very end, but near the very end. Yeah, I see it here. Page 395, 96, module 1207 and 1208. And this is a cryptic thing that I use only in emergencies, but it gives me this prompt of a hash mark. And then the numbered options that I can type are described on page 396, and there are various things that I can do. For example, 11. We'll check the memory to see if all the links are okay. If there's any weak links, if the lists have been clobbered, somehow it will have checked that. Well, it didn't find any problems. I guess they would like some of the house lights in the audience so that they can look at their own copy. Is it getting brighter out there? Can you give them some house lights in the audience, please? Okay, thanks. Now the option number 1 will print memory word of a location n in memory, well, I should find a location that's not 0. Let me try 580 and hope that it's not 0 and see what it is. It's not been it's been preloaded to 0. 581, 02. Let's see. Excuse me a sec here. I'm going to what's going on? Well, let's see. Going to try to find out which locations are not free. So 527 to 570 are not free. So I should be able to get 570 or something like that. 527. So let me try 527. Okay, so if I say 1 and then 527, 1 is my debugging command. It says print out memory word 527. Oh, that's 0 too, darn it. Well, here's one that wasn't 0. Okay, now print memory word is something that I can use that would print out a memory word in all of its possible forms. So memory location 528 is a memory word that can be interpreted as an integer as minus 262,144 on this particular machine. Or if it's interpreted as a glue ratio, it would be minus 4.0. Okay? And if it's as a scaled. If it's interpreted as a scaled, it would be minus 4.0 because I divided by 2 to the 16th. If it's interpreted as a glue ratio, it would be 0 because it has a 0 mantissa essentially. Now, the next line, print out that memory word as if it was 2 halves. And so to the left of the semicolon, it says 49152 equals 192:0. So the left half, it's either an LH field in this 2 halves. It's either a left half of 49,152, or it's a B0 of 192 and a B1 of 0. And the right half is 65535. Is that sort of clear? Now, if this memory word, was packed 2 halves, then the RH part would be 65535. And with the 2 halves, you have either LH, which would be 49,152, or you have B0 and B1, which would have been 192.0. And then the last thing on that second line is 255, 255, 192.0. That's B0, B1, B2, B3, in case you call it 4 quarters. Now this shows that this particular Pascal compiler packs these words. The one that I call right half actually is in the left half of the word. The thing that I called B0 in case 2 halves is 192, but B0 if it's 4 quarters is 255. I think it's the left half anyway. It must be, or it comes in somehow that way. So, but it doesn't matter how the Pascal compiler does that, since I'm never going to make any assumptions about the way Pascal does the packing. I'm always going, when I store something in with 2 halves, or if I store something in the B0 field, I'm never going to read out an LH field. Okay? But when I'm debugging, I might want to take a look at memory and have it printed out in this way to see what it would be like in different fields. Here's one of the places then where I did dirty Pascal. This is one of the few places in the code where it does read a memory word in a different format from the way it was stored. But I only use this as a last resort. I just built this in so that I could do so without having to do a lot of pencil and paper calculations on the thing if I had to otherwise. Well, I found out afterwards it wasn't that bad, because if I go back, if I type 0 now, I get back into Pascal debugger, and the Pascal debugger I could talk about mem 527, and I could say .int, and this debugger, 528, sorry, tells me what it is, and then if I wanted it with the RH, it would have given me 65535, and I could also ask for the .qqq.b2 field, and it would have told me what it is. So I didn't really need this print memory word very much, because I have it in the Pascal debugger. That does illustrate, however, the idea of a memory word with a little bit of redundancy. So I think by now everybody knows so much about memory words they want me to move on to something else, right? Okay. The format file that you dump out is all full of memory words. So the format that contains all of your strings, your macros, font information for quick preloading, the .fmt file, that is a file of memory word. And that's one of the reasons why we wouldn't expect it to be readable from one machine to another. Now, inside that memory, several arrays in the program are type memory word, but the big one is this mem, M-E-M. And That's the one that goes from mem base up to mem max inclusive. And inside of that, we do dynamic location up until a point called high mem base. And there's high mem base and low mem base, and the layout of memory is explained in modules starting at 156, and then the next few pages after that. The 156 gives really the layout of memory. That's on page 51. So the key place there is high mem base, because memory is divided once and for all into two areas, the low part of it and the high part of it. And the high part of it is used only for one-word records. And the low part is used only for records that are more than one word long. Now here again, I didn't use Pascal's heap or something. I programmed something from scratch so that I could control exactly how much memory was getting used here, and so that it would be more portable. Now we could do a lot of other things with it, same kind of reasons as for strings, but even more so now. The area less than high mem, then, as I said, it always has nodes of 2 words or more, and those above high mem are done in the simple one word at a time reservation. If you have a job that has lots of macros, macro gets stored in one word items. The item actually consists of the RH part is a link, and the LH part is divided into B0, B1. No, it's the LH part, which is a token, or a 16-bit representation of one token of your macro definition. So if you are running something with large macro packages, you want a lot of space above high mem base. The thing that put in the present, the old version of TeX, the thing that put big demands on things less than high mem base were boxes, and also the nodes that were made up intermediate to making paragraphs. For example, when I ran this TeX job on Sunday to print this book for you, I overflowed my memory below high mem base when I got to the index, and here I was 430 pages into this thing, and it crashed. Memory capacity exceeded, and the reason was that there was the word type had been used so often, and it came right at the end of a page, so TeX memory was already fairly full. And then along comes a paragraph that tells all the places where I used type in this program, and for each of those it built a very large break node so that it could optimize the index entry for type, which was also a trivial optimization if you looked at it, because all the 3-digit numbers, there would 5 of them fit on a line, and there was nothing else to do. But it didn't know this because it's doing a fancy ragged right margin and everything. So the memory crashed because it was overloaded there with boxes and things for the paragraph shape. Well, in TeX82, the paragraph nodes are reduced in size from 10 words to 3 words, and they aren't generated as often. So you won't need quite so much space there. However, if there are still if you had an application that was doing things with real long paragraphs, there you would need a lot of space below high mem base. But there's important reasons for fixing it once and for all at compile time, what this high mem base is, as you'll see as you get into it. So this is the way you have to make a decision when you compile TeX as to what high mem base is going to be. A high mem base is not listed in that list of compile time constants in the module 11, because if you change high mem base at compile time, then you can't run a format file. You have to also change your FMT file. See, the FMT file is going to start loading macros at high mem base. and compute some other things that go into the memory there. But you're allowed to change mem max at compile time, and it won't affect your format file. So you can increase the size of the memory up in the macro region, up in the upper area. Just change it in the constant section of TeX, recompile, and you've got more memory up there. But if you have to change high mem base, then you're going to have to also run AnyTeX again, and make another format file. The constants that you're not supposed to change at compile time are listed in module 12. So the constants in 11 are given as Pascal const type constants. In module 12, the constants mem base and high mem base are defined as web macros. Also, hash size is another one that's defined there. So if you want to change the size of the hash table, certainly you can't preload your hash codes if you change the size of the hash table. Many of the other things, though, can be just changed, and the FMT file will still work even though the size has been different. So you can increase the number of fonts, you can increase the number of parameters, increase the size of your buffer, increase the size of your string pool. Most of those things can all be changed without recompiling AnyTeX. That's the high mem base, then separates the dynamic variable size memory from the other part. Now the variable size memory starts out with a few words that are in fixed locations. And I guess here I get to try out this pad and see what happens. Or should I try the blackboard? I think the blackboard might be better because everybody be able to see. So here's the dynamic memory, and here's your here. I got you. Okay, I thought I had better light there, but it's okay. So here's your dynamic memory. This is mem, and I put mem base here, and mem max is the largest, and then there's high mem base somewhere where you decide is a good place. If you compile with the stat option, then it tells you exactly what the maximum amount of memory you've used of both kinds is for each job, and also within a particular page, so you can get a feeling for what would be good for the kinds of jobs you're running. Now, there's another location defined in this section on the memory allocation called first mem and second mem, and these are where we actually do the dynamic locations. In between here, we have fixed locations set aside for things that I can refer to by fixed addresses. I know they want to be somewhere in mem, and I also know that I'll always need them there, so I always put them there. So right here, for example, we put the specifications for glue that like a fill glue or zero glue, things that people can say when they say hfill. Then it will refer to one of these words. We know we will always want an hfill to be present. In this area, I have one-word nodes that I always want to be present. These are typically the heads of lists, so that they'll have a link field, and this will be starting to point to the first item on a list. And it's good to have another word that starts that list. It makes a lot of the algorithms simpler, so they don't have to consider the empty case as a special case. So this is the high mem base to second mem. And then all of these other areas, from first mem to high mem base, this is 20 up to high mem base. And then this is about, I don't know, a dozen locations in here, all the way up to mem max. This is all dynamically allocated. Now, the easiest thing to describe is how we allocate memory in this part of it. All of these words are of type 2 halves. Remember that type 2 halves had an RH part and either a B0, B1, or H8 or LH in it. Oh, now the two halves here are the RH part is always called link. And so typically our one-word nodes will be linked together in a list that we draw this way. In the link field, I call it link, and so there's a definition that link is the same as RH. Now, there's a pointer. There's a global variable called memend, which tells the largest location in this memory that you've ever seen, that you've ever asked for. So TeX never bothers to initialize this part of it. This might be gobs and gobs of memory. It's memend is the largest one you ever needed. And it points to and there's another one called avail, which points to the first one that's not being used right now. So if avail ever gets to be empty, a null pointer, then we increase memend by 1 and get the new location. Otherwise, we never look at memend. And but otherwise, avail is pointing to 1, and that one is pointing to the next one that's available, and so on. A typical way of keeping track of which things aren't currently in use. So when something is recycled, instead of doing a garbage collection, we have the algorithm that immediately makes it available. And then when avail becomes null, and we need another one, then we try to move memend. At that time, if memend equals memmax, we're out of luck. We've run out. Okay, now those algorithms then are described just before the discussion of memory layout. Dynamic memory allocation starting at module 110. That's right after the description of memory words. And in that section, it talks about the way avail is handled. So let's see, that's the bottom of page 39. And you might see my finger here, avail, link of avail. These are the available locations terminated by null. Now I never say 0 for a null link. I always say null. And I define null to be membase. So it's the same as the address here of the first word in memory, which turns out to be also the same as the where 0 glue is stored. I never make use of this fact, but it's true. But when I say null, this means I'm thinking of it as a null pointer. If I say 0 glue, that means I'm thinking of that as the address where 0 point plus 0 point minus 0 point is stored. And if I say 0, that means I'm not talking about a memory address at all in my program. Okay, now, so globals for avail and memend are defined at the bottom of page 39 there in module 113. To get a new word, I say get avail, and we have a function says that returns a pointer. And the word pointer is a synonym for half word. However, it's only used when I intend it to be a pointer into either mem or one of TeX other big tables. Could you show that on the screen possibly? Here is the getAvail function. Yeah, your camera is pretty good. The getAvail function that allocates a single word node. And so that's the simple algorithm that I mentioned, except that you see we have to also always be careful of errors. And so P is set to avail. If it's not null, that's good. Then we just set avail to link of avail. Now avail is pointing to the next available one, and we've reserved it. Otherwise, we look at memend, and we hope it's less than memmax. Go into virgin territory. So if it's less than memmax, that's great. We increase memend, and that's the value P that we're going to get for this pointer. Otherwise, we call a procedure called runaway. Now this is a procedure that will come in and give an error message saying, do you have a runaway argument? Because that's one of the most common reasons for for running out of memory at this point is if somebody forgot a right brace, and it might be a parameter to a long macro that doesn't have any protection against right braces missing. And here we would like at least as long as we're going to abort the job for running out of memory, we're going to at least want to point to where the error was, so it won't happen again. So there's a runaway procedure that will give a essentially appropriate error message there, I believe. Then we set link of p to null before we return get avail. Whenever we get something from that procedure, it's going to have its link field null, because if you ever want it to be something, you want it to be null, and you almost always want it to be null when you're getting a new word out of this memory. Then there's something that would be commented out unless we were maintaining statistics, and here's what would slow it down, because we have to get available things rather often. So increasing this counter, seeing how many words are currently in use, and then get avail is the value of the function is returned at this point. Now to free avail, we'll put something again. I just wrote a macro for it. I didn't want the procedure call overhead particularly, so it was only needed about 5 places in TeX, and so why not repeat the code each time instead of calling a procedure? So I have free avail of that pointer, so we just do the opposite process. We plan a link field to the previously available one. Avail now points to the newly available one, and we decrease the number of things dynamically used. There's no other way to get available one-word nodes. You have to call one. You have to say get avail or free avail. It's not allowed to do this yourself. And, it comes through. The next procedure is something that'll take a whole list and free them all up. Now, so that's simple in the one-word part of memory. In the variable word part of memory, there's a kind of interesting method used, and I'll go to the blackboard again, switching this multimedia show here. Does somebody have the time, by the way? I want to try to pace myself. Actually, I have it on my screen here if the computer isn't down. Yeah, 2:55, you're right. Okay, so in this area of memory, in this area of memory, every time I get a variable size cluster of nodes, I make sure that the link field in the first word is something unequal to mem max. It's never equal to mem max. Remember, the never equal to max half word, because we made sure that mem max was strictly less than max half word. So this is something that would never occur as a link field or a pointer. If this was equal, but the ones that are available are going to be flagged by having their first word, a link field here, as max half word. Now, so we can store any data here except that one bad one, and then the rest of the format is completely free. But going to this is in use. But if it's free, then we put max half word here, which I can just indicate by all ones or something like that in binary. And then we put the size here of the free area. And then I have an L link and an R link in the next word. And this is a doubly linked list of free cells that goes around in a circle. And then the rest of the words are unknown. Now, if I want to free something up, I simply stamp its size field here. I have to know how big it is when I'm freeing it, and then I link it into the circular list. There's a list of all these nodes that are free. And when I need to find a new place in this memory, I go around this list until I find one that's big enough by looking at the size field. But before I check to see if I found a place big enough, I also look at the one right after it to see if it's also free. If it's also free, then it'll have ones in this field here. And then I can combine these two at that point, and I keep doing that until I get to a place that's followed by a non-free one. Might be preceded by a free one. I don't care. I'll get to that one later if I really need it. But I look ahead and collapse it at this point, and dynamically this works out very nicely. And then I get then I see if the size is right. If it's big enough, that means that it might fit perfectly. Then I can just allocate it and take it out of its list. If it's one too big, I can't do anything with it because I'm not allowed nodes of size 2, of size 1 in this area. So it has to be at least two larger. If it's at least 2 larger, then I allocate the top part and I decrease the size of this one. So that's the algorithm that's explained there in the next part for variable. For getting variable size records. The important thing to remember is if you're implementing any extensions to it, make sure that you put some kind of a link field or something in the first word here that could never possibly be all ones. That's a mild restriction, but it could certainly be violated if somebody didn't know it. Okay, well, now I'm running a little bit short though because I wanted to tell you what goes into these lists, and but I got through most of the main ideas because we talk about the info. I guess in the one-word section of memory, I always call the left-hand, the LH part, the info field, and the right RH part, the link field. Then something that's also rather commonly used in the program is an L-link and R-link field. But these always refer to the info and link parts of the second word of a multi-word node. So if I ever in my program say L-link, I'm talking about the left-hand part of word 2 of something that's at least 2 words long. Now, all of these things that can go on then in a horizontal list are indicated somehow and linked together. So if I have a list that has 100 items in it, I'm going to have a pointer to the first one somehow. Its link field will link to the second one. Its link field will point to the third, and the final one will point to null. I use a circular linking like this only in the list of available cells for the variable size memory. But the other lists are always, well, there's only 1 or 2 exceptions, almost always end with null. And I have to tell what kind of a thing what kind of thing I'm doing. So there's a little bit of a problem because I want to pack a link field in a word, and I also typically have a font and a character. Font is 256 possibilities, that's a quarter word. A character is 256 possibilities, that's another quarter word, and my link is a half word. I've used up my 32 bits. So here we have a great solution due to I don't know what combination of the two of you, but they realized that just by looking at the address of the word, I could tell whether it was in the one-word part of memory or the variable part of memory. So if it's up in the one-word part of memory, I know it's a character node, and I don't need to look at it any further. I know that that contains font and character information. So up here, anything up above high mem base is going to have a link in this part, and then it's going to have a font and a character in its B0 and B1 parts. So this is called the font and character fields. So as I'm going through a list, I can check to see whether the pointer is high. Then I know that it's a font and character. Saved a bit that way. Now, if it's not, then we have a type field. And so we have a type field and a subtype field. The type field tells what kind of a thing it is. Is it a box horizontal, made out of a horizontal list? Is it a kern or whatever? The subtype is further information relating to the type. So the type field then is something that we have room for 256 different types. I'm only using about 30 of them. The subtype field is often not used at all. If I was implementing this on a microcomputer, I could do something different about the organization of the memory. Since all these words up above high mem base are half words, I could allocate them as 16-bit, as two 16-bit arrays, which go from high mem base up to mem max, and then I could implement from mem base up to first mem as 16-bit words, and make, instead of a memory word, I could use, I could devise something so that if this would ever come out to some other number of bytes, then I would save a little bit of space in here. I don't think that would save a great deal, but it's a possibility for change. In other words, if you change some of these macros, you would be able to run the rest of TeX just by changing the way it refers to nodes in memory with some other memory organizations that would be equivalent. However, I don't think that in typical use you'd gain a great deal over what we have right now. Now, each type, so if I'm looking at something in a thing, I look at the T field, it tells me what type it is, and the type will be one of these things listed starting on module 129. And there's just a great number of definitions there, following all of the English language words. It says H-list node is 0, and so the type field will be 0 in such a case. Box node size is 7. This is declared as a macro, so that when I free a box node, if somebody chose another way of storing this, and boxes were some other number of words, then you would only have to change this macro in this one place. The width, offset, depth, the second word of a box node is its width as a scaled number. That's defined here. Width of something is mem of that plus width offset dot sc. Okay, that's the width of a box, the depth of a box, height of a box, shift amount of a box. These things are explained in words above it. Now the different things we can have is our H-list node, V-list node, rule node. Turn the page. We get inst node, insertion nodes, mark nodes, adjustment nodes for the V-adjust operation, ligature node, discretionary node. All of these have subfields that are explained what their function is there. I might go into that a little more next hour. The what's it node I mentioned in the lecture yesterday, that's not type 8, and that's for extensions. In the subtype, you look at the subtype of a what's it node, and it would tell you what kind of a what's it you have. There's a math node that begins and ends math formulas, glue nodes, which are pointers to the actual specification of glue, kern nodes, and penalty nodes, and some more coming up later, unset nodes and things like that. So the various different types of nodes. And I describe this all in words so that you know what they represent. In order to reinforce that, whenever in this program, whenever I define a complicated data type, I usually follow that by a bunch of programs that print out that data type in symbolic form. So at least you can get an idea as to some programs that use this data structure and how a safe way to refer to the data structure is. Because if you're going to have a program that's going to print out what's in a node, you've got to be able to, it's not only, this printout is not only going to explain what's in the node, but the program is going to use the right protocols for accessing the node. So this whole section called displaying boxes is really worth reading if you ever want to know what's in a box. We looked at one of those examples before. Display a node P. It says if is char node, then print font and cherry. So, but if you look at these codes, you'll see that this is the way you're supposed to look at the data structure by using the macros in these routines that display boxes and glue and so on. So the programs not only will give printouts then when you have to find out what's inside of TeX instead of looking at all those bits and checking against the macro definition saying, what was type 3? Not only does this give you a program that does it symbolically, but it also, the program itself shows you as a paradigm of how to write other programs that access the data structure. Any questions on that before we adjourn? Okay, thanks very much, and I'll see you in 24 minutes.